So welcome to the MICASA-SUCASA talk. Now, I've never been good at introducing myself, so I did what any hacker does when presented with a new problem for the first time. I looked on Google. So I searched for presentation icebreakers, and one of the top results was enchant your audience with statistics. Now, I'm not going to subject you lot to a presentation that starts with statistics, so instead, I'll start with a confession. The last time I was on stage was 20 years ago. I was dressed as a donkey for my elementary school Christmas party. And unfortunately for you guys, I don't have a picture of the event, fortunately for me. I'll try and bring the same nervous energy to this. Now, hopefully the ice is broken. My name is Elliott Thompson, and I'm a UK-based principal security consultant over at SureCloud, and I believe I've spelt it wrong on this slide. Come on. Nope, that's the donkey. That's me. So, that's my alphabet soup there. So it's OSCP, CTL over in the UK, as well as 2 CVEs, so a privilege escalation in Beyond Trust's BombGuard remote support application, and a browser-based remote code execution in the VTech Android tablet. Now I'll jump onto the meat of the presentation. So the core assumption that MICASA relies upon is if you're connected to your own network and browse to 192.168.1.1, then connect to my network and browse to the same IP address, as far as your browser is concerned, they're exactly the same thing. Now, this alone certainly isn't like a new discovery, but we can stack a few other behaviors together and make something exploitable. So, digging deeper into the internal IPs thing. So, I said that browsers treat them the same no matter what network you're on, but what do I actually mean by that? So, I'll go through 3 examples. The first is caching, then cookies, then JavaScript. So this is just a rough example of a sticky captive portal that I built. So normally any pages served by a captive portal are aggressively not cached. The last thing Starbucks want is for you to keep seeing the captive portal page after you've signed in. And when connected to my Starbucks network, I serve a page with the cache control header set to a max age of 1 year. So when you go home back to your corporate network, you'll keep seeing that same captive portal. So that kind of quickly demonstrates the caching side of things. Now on to cookies. So the next thing I want to kind of go over is the behavior of cookies in this kind of same situation. So cookies that are set by a login interface on one network are automatically attached to requests for anything accessed through the same URL on a different network, at least until the cookie expires. I know to many of you, especially on the website, that this is like super obvious expected behavior, but stick with it. The fun stuff is coming. So here we have pfSense running on my home AB12 wireless network. The page is hosted on 10.10.10.1, and when we log in, we see the PHP session ID is kind of stored as expected against the kind of domain 10.10.10.1. So far, so standard. But if I then rush out for some junk food and connect to this fake McDonald's open Wi-Fi network, in this case, the fake captive portal happens to be on the same IP address as the pfSense machine. So it means the browser sends our pfSense PHP session ID to this totally unrelated captive portal. But so what, right? So sure, McDonald's now has a session token for my pfSense box on my internal network. To actually use that session, they'd need to get inside my network. And there's another problem as well. So we have to contend with how long these cookies are going to last. So cookies can be set to expire in like a specific set amount of time or at the end of a session. And the definition of kind of session varies between browsers. It gets a bit fuzzy. So Chrome, when you close the browser and all kind of profiles that you've got open, that's when the session kind of ends. For IE, it's the same kind of without the profiles thing. You have to close all the windows down. And then the kind of sessions are cleared. For Firefox, it removes the cookie as soon as the tab is closed. And when I tested it on Android, the flag was just completely ignored. It was just kept for as long as they needed it. So the window of a cookie being available is either going to be the date specified in the expires flag, or kind of when the session ends or when the browser closes. And on the subject of browsers being closed, so these days it's fairly common to leave browsers open for a long period of time, especially if you've got like a laptop. And in fact, if any of you have seen these arrows in Chrome, like, feel shame. Like the green one is Chrome has like needed an update for 2 days, and you just left it, not updating it, not closing Chrome. And red is like a week. You've left Chrome needing an update for a week without restarting it. So it's safe to say, like, I'm sure some of you have probably seen at least one of these arrows. But it's safe to say that browsers that require the entire process to be stopped, we can rely on users not closing their browsers, meaning the expires session cookies are kind of fair game, as well as any cookies with either no expiration or some expiration kind of far in the future. But of course, we're still limited by anything expiring server side as well. Now onto the last of the 3 browser behaviors. Here we go. In the previous cookie example, we first started on my safe home network and then logged into so we started on the safe home network, logged into pfSense, and then ran to McDonald's and joined the unsafe network. But what if we reversed the order? So if instead the victim starts somewhere unsafe and then connects back to their own secure network, could something be left behind? And the answer is yes. I wouldn't be standing here if the answer was no. So instead of just serving the McDonald's captive portal on 10.10.10.1, let's hide some JavaScript on the page. Now, I totally accept this is some hideous JavaScript. I just tried to collect as many deprecated functions as I could. And line 2, so I'll go through the important lines. So line 2 just gets the CSRF token from pfSense on the new OpenVPN client page. Line 5 pulls the token out. Again, it's horrific. I'm sorry I've done it this way. I apologize to any of you that deal with JavaScript. And lines 8 and 10 just build a malicious post request and then submit it to pfSense along with the CSRF token. And the post request just does something really simple. It just creates an additional OpenVPN user. So here we are. So now we're connected to the McDonald's free Wi-Fi connection, McDonald's free Wi-Fi network, and in the background, our page has loaded that malicious JavaScript, and it's cached for a year. And that JavaScript will be continuously running while they're on this captive portal network, and that pfSense request that kind of get to the OpenVPN stuff to grab the CSRF token, that will be continuously failing until they go back home again. So then when they try and log into their pfSense web admin interface, they'll instead see the McDonald's captive portal page and probably think, huh, that's weird, hit refresh, and they're back into their kind of standard dashboard. But by this point, it's already too late. That malicious script has executed, and we have a new VPN user added into it. So as the attacker, we can connect straight into their internal network without ever having to have connected in the first place. And of course, if we actually check the VPN configuration, we can see all the malicious changes. So I just want to stress, it's not a vulnerability in pfSense. This was just an example I chose. We're just using the standard interface through JavaScript. The attack will work against just about any interface. Anything you access over IP address, at least. So that goes over the 3 browser behaviors that we're going to look at. So caching, cookies, and JavaScript. They're all shared between devices accessed through internal RFC 1918 IP addresses. And the reason behind it is pretty simple. Browsers aren't really aware that the network you're on has changed. So it totally makes sense. For origins like google.com or vk.com or whatever, they only really exist once. So browsers that use those differentiate. They use the kind of the domain to differentiate between things like caching, cookies, and like just resources in general. That's what they use to differentiate them. There are a couple of exceptions, like cookies being scoped exclusively to certain pages or paths, or specifically to HTTPS connections, like with a secure flag. But anyway, on to the second major component. So Karma. So when writing this presentation, I remember the Karma attack as being like a super recent thing that wouldn't need any kind of explanation or introduction. But after checking, my definition of recent made me feel so old. So 15 years ago, Dino Dezovi and Sean McCauley found that you can effectively coerce Wi-Fi devices to connect to networks that you control without user interaction. So how does the Karma attack actually work? So when you connect to a network and allow automatic reconnection to it, whenever your device is not connected to that network, it will send out probe requests asking if any of those networks are nearby. If one of those networks is nearby, the access point will send a response saying, that's me, and start initiating the connection. And Dino and Sean found that you can boot someone off you can trivially boot someone off their own wireless network with a deauthentication frame, and then respond to those probe requests asking for kind of network access as, yeah, sure, I'm Starbucks_Wi-Fi, that sounds about right, connect to me. It's worth noting that it only works on open networks. So since encrypted ones require the pre-shared key to be known by both sides. So I'll quickly do a quick go through. So this is what the Karma attack lets us do. It lets us pull someone off their secure network and temporarily bring them to our dangerous network. So in this illustration, we have two separate networks with all clients connected happily. We send the deauthentication frame, a spoof deauthentication frame, effectively telling the client that, hey, router says right now you need to disconnect. And then the client dutifully just does as it's told and disconnects. Once the client's disconnected, it starts searching for networks, anything that it remembers. But that searching involves shouting the names of all the networks it's previously connected to, hoping that one of them will respond. So we respond to all of them. So if you're looking for Starbucks_Wi-Fi, yeah, sure, that's me. You mean Hilton Guest? Yeah, me too. As long as those remembered wireless networks didn't require a PSK or a certificate or whatever. But now the target's on our network, thinking it's on Starbucks Wi-Fi or whatever. But how does that look to the end user? So it isn't super obvious that you've disconnected and reconnected? In most places, you'll have like a couple of seconds of like the connecting animation, followed by the connected sign again. And if someone clicked on the wireless icon, yeah, sure, they'd see that they're now on Starbucks_Wi-Fi, despite being in their corporate office. But most of the time, there's nothing that's going to be plainly obvious for them to see. Here we go. What's it? Okay. But now that the target is connected to our network, we can poison the cache and display whatever pages we want. But that's not particularly useful to us while they're connected to our network. Anything I drop down can only be used to attack me, and I don't want them attacking me. I can do that already. But before moving on, I just want to stress that obviously I had no part of discovering Karma. That was Dino and Sean. I was probably a teenager at the time. But on to the next bit. So at the start, I demonstrated that we can add JavaScript onto internal IP pages that uses onto internal IP pages if users connect to our network. And we demonstrated we can use Karma to pull victims onto our network, or pull targets onto our network. They're only victims once they connect. While they're connected to the network, we can poison anything we want, but none of that matters until they're back on their original network again. So like a rescued animal, we want to release them back into their home, although unlike a rescued animal, we'll be sending them back with more parasites. And this is by far the simplest part of the exploitation chain, though it is still absolutely critical. So all we need to do is boot them off our malicious network, and hopefully they'll automatically find their way home. So booting them off our initial fake network is super easy. We can just disconnect ourselves, and the poor device will get confused. It'll start looking for its known networks, and this time we shut the hell up. And then target's back home again, along with our JavaScript payload running, and we can attack the router or whatever it is that we've poisoned earlier. And to the target, this looks exactly the same as it did before, a slight brief moment of connecting and no internet access, followed by connected back to the home network again. So in summary so far, we can use the Karma attack or just wait and pull someone onto a fake captive portal, poison a particular IP address domain or RFC 1918 domain with JavaScript, then have the target go back to their own network, allowing the JavaScript to execute in the context of whatever internal network device that we just poisoned. But we're not done just yet. So now we reach the final and most complex component, which is the automation side of things. Now, This component exists purely to solve two specific problems with the chain of exploits so far. So the first problem is we need to know the IP address of the system that we're targeting. And the second problem is we need to know the HTML/DOM structure of whatever it is we're targeting. But we can overcome both of these. So starting with the IP addresses issue, we're going to switch from our kind of one-shot sniper method and go thermonuclear. So RFC 1918 defines all internal IP addresses. And in total there are roughly 17 million across these three ranges. Cool, so let's hit them all. Let's try and poison 17 million IP addresses as quick as we can. And no surprises that does not go well. I tried to, but yeah, every single browser you try to submit 17 million requests for immediately just doesn't go well. But that's a surprise to no one. But realistically, we don't really need to poison every single one of the 17 million addresses. So techspot.com and a few other sites listed a ton of common default router and firewall and switch IP addresses. So let's start with those guys. So the IPs have been helpfully separated by vendor, but we don't really care. So instead, we just want the unique IPs. So I started with a list of about 500 default IPs across various different sources and various different websites, of which 54 were unique and 53 had the right number of octets, which sounds like a more reasonable starting point. So these were the most common 53 default device IP addresses, which is a good starting point. Now, if you guys look closely, can someone spot something which doesn't belong here and just shout it out? Yeah, there we go. So there's one in here at the bottom right which starts with 200. So 200.200.200.5. So when I first saw this, I immediately thought, it's just a typo. It's clearly just a typo. No one would really do that, right? But then before just deleting it from the list, I thought maybe I should check. It turns out, TrendNet released a device a good few years ago that the TEW432BRP, which used those .200 IP addresses in its management interface. And I checked the IP address myself to see if it was like a range that was defined for like documentation or something kind of something unusual that I hadn't seen before. But no, it was a Brazilian ISP. So the TrendNet are just handing out public IPs for this Brazilian ISP to their internal network devices. It gets better too. So it's not just that one management interface. There's like 200 DHCP addresses or 100 DHCP addresses that are owned by this Brazilian ISP that are just being handed out to internal TrendNet devices. My favorite part about it as well is, so I mentioned that it's the V3 of the TrendNet device. Like the V4 had it as well. Like this was a mistake they made twice. But Shodan showed that there were multiple devices that were happily listening on the address as an alternative interface. Although I didn't get any responses from the real IP address, unfortunately. But moving on. So now we have a list. Now we have a list of 52 RFC 1918 IP addresses. And it was interesting to see there weren't any common defaults in the 172.16 range. But just to make sure they all get loaded into the browser cache, the first task was to create some sort of page kind of orchestration layer which submits a request to all of our 52 targets. And a few lines of terrible JavaScript, and we're ready to go. So all this does is iterate through like a fixed list and send HTTP requests. It's not pretty, but it was quick. And it can also, we can just add additional stuff to the lists at any point. So we can add kind of all of 192.168, like the /24 of .1 or the /24 of .0, whatever's the most common in the particular engagement. But cool. Now we're submitting requests to all of these IP addresses, but we still need a way to provide HTTP responses for them all. Now, if we were just doing DNS hijacking, that would be super easy. All we'd need to do would be to provide a DNS server through DHCP and then send anything through to a particular IP address that we controlled. There are modules and there are things that exist to do that. But we can't do that with RFC 1918 IP addresses, since we expect them to not require DNS. But the simplest option, rather than sending specific routes through DHCP, was just to use IP tables. So just to quickly break down how this works, so I've got a server running on 172.16.214.1. That's the first time I've said that right first time. And any client that gets pulled onto my network gets assigned a DHCP address in that same /24 range. And the only reason that was chosen was because it seemed as far from one of the defaults as possible. So this IP tables rule effectively says anyone using this gateway, so anyone who's joined my network that attempts to connect to 192.168/16 or 10/8, translate that to the server's gateway IP address, where we've got an Apache server or an Nginx server listening. So anything we host on that 172 IP, kind of our server IP address or our gateway IP address, is going to be kind of responding directly to any requests to those RFC 19 AP or our default IP addresses. But now that we've got our orchestrator payload done, that submits, so we now got our orchestrator payload which submits all the requests to the internal IPs, and we have now an ability to respond to them all. But at the moment, we're just providing the Apache it works 50 times. So that's no fun. But before I get onto the actual payload, I'll quickly mention a fun optimization technique that almost all of you probably already know about, but I found it really interesting at the time, which was if you go to, say, google.com, and their page imports a piece of JavaScript from, say, the Cloudflare CDN, then you go to a totally different website like LinkedIn. If LinkedIn imports the same script from the same CDN, your browser doesn't need to make a request for it, it will just load it locally from its own cache. So instead of us having 10,000 lines of JavaScript sent 50 times, we can send it once, cache it, and then have all the other pages look at that particular cache. So the number of requests that we're sending won't change, or the number of responses that we're sending won't change, but the data goes from megabytes to kilobytes, which is what we need to kind of help get increased from 50 to anything more than that. So anyway, that's the optimization. Onto the actual payload. So at the current stage, with what we've been through so far, I need to create a payload for every different device that I want to target. And now targeting projects like pfSense, that's fairly easy since we can just download a copy and build our own payloads. Similarly, router interfaces, they're pretty easy too, if we can just buy one of the routers off eBay. But there are plenty of devices that we're not going to be able to have this level of access to. So instead of building a million different payloads for a million different devices, I needed a way of writing a single piece of JavaScript that was useful no matter what context it was running under, something that could be used to attack any device in any state. So the first step was relatively easy. If the root page looks like a login interface, the next step is pretty easy, like try and log in. And detecting login in pages, thankfully, isn't hugely difficult. So there are definitely plenty of options when it comes to detecting login interfaces, but most of them aren't going to be super reliable. So let's kind of rule them out one by one. So firstly, the obvious stuff, the contents of things like titles, paragraphs, and divs, they're expected to change based on the device itself. So we can rule those out. But that's the first step. The next is the form action. So credentials could be getting sent to any URL, or it might not be in the standard location. It might not be the form action at all. And same with the various names of the inputs. They could be something specific to the device, or it might be just in a different language. But now we're narrowing it down. So with the input elements themselves, the type value is part of the HTML spec and is unlikely to be custom. But we don't know whether the interface is going to be asking for a username, or whether the submit button is handled elsewhere, or you just hit enter or whatever. It could be missing, like I say, it could be missing entirely. But we can expect in 99% of cases for there to be an input somewhere of the type password if it's a login interface. So now we have our first check, which effectively fits in our if statement. So if it's a login page, what do we want to do? We want to log in. And we don't necessarily have credentials, or we might not necessarily know credentials, but we can just throw like a brute force. It's on the inside of someone's network. We might be able to just log in with brute force, or it might be already authenticated if there's already a session that's active. But what do we do if the target device either doesn't require authentication, it's already logged in, or if the brute force attempt somehow succeeds? Now this is where it gets a bit tricky. So if we see a router, we might want to add, like we did before, with add a VPN connection, or extract or change the PSK. If we see a firewall, we might want to punch a specific rule through. Or if we see a CCTV camera, we might want to just turn it off entirely. But the answer? We can send the logged in interfaces to an off-site neural network trained to identify the most strategically relevant next steps when confronted by any device interface. And by that I mean send it to you, the human. And that was stolen from XKCD. So welcome to the most bizarre stock image I've ever paid real money for. Now, grabbing the authenticated device pages isn't trivial, but thanks to the Beef.js project, all the hard work has already been done. So it was surprisingly easy if you ignore the ridiculously hard work that's been put into the Beef.js project. So to quickly explain that particular project, it was designed as an cross-site scripting exploitation framework by Wade Alcorn. So the idea being, if you found like a stored cross-site scripting vulnerability on a page, you can build a payload which includes the Beef JavaScript hook. Then anyone connecting to that page with the hook loaded effectively gets the script running in their user context on their machine, with their session hooked as well, along with features like Metasploit module integration and integrated browser exploitation, that kind of stuff. It's a fantastic piece of kit. But the killer feature we want to use is the ability to tunnel our requests through JavaScript running on the target's browser. So within the context of whatever interesting device that we're targeting, when they're connected back to their own network. And this means that when one of our poisoned pages is active, we get a callback that we can tunnel straight to the device through the HTTP proxy through Beef.js. So to clarify, the JavaScript tunnel itself runs over the internet. So we as an attacker, we don't necessarily need to be on the inside of their network to do this. But enough diagrams. I'm going to try and see if you can. So we'll get a video result of me frantically trying to get this working like an hour before the deadline to send it to Nikita. So I will try and get this on screen. I taped my notes over the touchpad on the laptop, so this is the most awkward thing. Here we go. Can I full screen this? Yeah, cool. So here we see the victim device on the right, and then two laptops performing the attack on the left. So the one on the far left is performing the deauthentication and the poisoning, and the one in the middle is just it's easier to show two screens at once, and that's the Beef hook effectively. So here they are, browsing a still HTTP MSN.com. And then we do deauthentication. So then we boot them off the home network while they're browsing Game of Thrones. I think I spent too long scrolling through this, but we're on the journey now. You're all in it with me. So after a couple of seconds, they should be getting disconnected from their home network, and then this is the Karma stuff. This is just the default Karma getting pulled onto my network. So there they are, disconnected from their home network. And then it should already be connected to the fake McDonald's Wi-Fi stuff that's getting automatically responded to. Again, it's just Karma. So far, it's just Karma. Yeah, as they're loading pages. So now I think after a page refresh, the Beef.js hook should be in. So it's not the Beef.js hook itself that I'm loading in. It's that orchestration JavaScript which is loading 52 separate Beef hooks on those various different router IP addresses. So if there are session cookies, it's hooked into that. But as far as the user's concerned, they're just seeing whatever unencrypted page that they're already on. There we go. So we've got the beef hook there against the particular router IP address. So this is the Fritzbox login, the Fritzbox router interface. So in beef, you just like right-click and set like kind of use as proxy. This is like 3 in the morning, so forgive me for this not being the most kind of nicely cut together thing. So that as they're browsing through, hopefully a long article to give you as long as possible to interact with their stuff, they've been sent back to their home network again. So now they're back home with that JavaScript running on that page, or any pages that were unencrypted that were opened. And now if we go to, so this laptop again, it's completely not on their network at all, but it's proxied through that JavaScript running on the MSN page. I hope it works. I think it worked at the time. There we go. So that's their internal router login interface over the internet through JavaScript. I mean, it's all thanks to beef, but it meant we can now kind of we can change the PSK, we can do whatever we want on their internal interface. But so there are things that it won't work on, like if there's a password or whatever on the device. But I tried it on an engagement fairly recently, and managed to access the data center fire suppression and HVAC system. It wasn't quite fully authenticated, but the guest account did have write access to everything. Get back into the presentation. Full screen. There we are. So that was the video. Now, so this is the project itself. So at the moment, it's by the end of DEF CON, it'll be up and public. At the moment, it's a combination of bash scripts and apologies. So I'm hoping in the next week or two, it should be kind of a nice, relatively seamless piece of Python. But at the moment, yeah, bash scripts, apologies. I'm sorry. One more sorry to add to the pile that are already there. Just on another separate quick note, something that was kind of funny. During this, I found that so each of the different browsers, if you've got, say for example, you've got a router login interface, 192.168, whatever, you've got your username and password stored, like remembered in Chrome or IE or Firefox. In Firefox and IE, when I tested it, to use the stored credentials, you needed to click from the drop-down and select your username, and then it would populate the fields, and then it would be available in JavaScript and DOM. With Chrome and Chromium, it was automatically populated, but you needed to interact with the page in some way. So if you like kind of left-clicked anywhere on the page, then the credentials would be available in DOM. So you could, like, there was a demonstration where you could have like a captive portal that stole the credentials, that the inputs didn't need to be visible. They could be kind of hidden away in CSS or whatever, so you couldn't see them. On Firefox, you needed to click on it. If they weren't there, you couldn't click on it, so you couldn't use it. But on Chrome, you could. You could just, as long as they clicked somewhere on the page, then you'd have them have the credentials that you could replay back again. So I submitted it to the Chromium project, and we got a kind of, it was a back and forth, but then the overall consensus was, yeah, it's a usability. The idea is it's meant to kind of make it easier for people to kind of log into stuff rather than clicking on drop downs, and completely agree with them. Like, love the guys over there. But then they fixed it. Like, but I guess it was just like an unrelated thing. So it was fixed like months and months later. But anyway, onto fixing it generally. So we've seen that it can be realistically exploited, but how can we defend against it? So the method that works best in enterprise environments is accessing devices through DNS names, configuring trusted certificates, the standard stuff that we do in enterprise anyway. But most importantly, disabling the HTTP interfaces, especially if those interfaces work over like direct IP address. Like if you can connect over IP address directly, then it's worth disabling them. Especially for the weird and wonderful like kind of like the SCADA, I say SCADA, like especially like the weird and wonderful random stuff that's on the network. And for home users and residential vendors, simply disabling the HTTP interface entirely and having only HTTPS listing, it should be enough to stop the attack working on a mass scale, since no one is clicking through, or I hope no one's clicking through 50 separate certificate warnings on the same page. But it still means it would be possible to target a specific device, but it defangs the attack significantly. Another potential is the wider adoption of IPv6. Since there are so many more addresses in IPv6, local addresses don't necessarily need to be shared between networks, and NAT isn't really, NAT doesn't really exist in it. So, but if vendors still use like a common set of defaults instead of using kind of unique ones, then the attack could potentially still be viable. And the final one is WPA v3. So based on the spec and what kind of a few other people have been through, so far the Karma attack still looks to be technically possible. So protected management frames are enabled by default, so you can't trivially boot someone off their own network. But there's still the potential, as far as I can see, for kind of just the good old-fashioned signal-to-noise ratio jamming. And as far as I understand the spec, open networks are still a thing. So keys are generated and negotiated, so there's no kind of unencrypted communications, but there's no trust on first use mechanism. So it might still be possible to, if, for example, you connect to McDonald's_Wi-Fi and connect to a different McDonald's_Wi-Fi, there's nothing there saying this isn't the same network that you've seen before. But it's largely conjecture anyway. Like I don't have any WPA3 devices, and this is based off like other people going through blog posts, other people going through the spec, and me reading their blog posts. So it roughly makes sense. And that brings us to towards the end of the adventure. I think we have a few minutes left on the clock. So if there are any questions.